Hey everyone, welcome to our 7th edition of EBNEO Journal Club. And today we're going to be talking about p-values. This is one of those areas that I think over time, at least for me, I've really changed the way in which I consider these, particularly from what I learned as a trainee. And I think we're going to have a really enlightening discussion today. And I'm happy to welcome Souvik. Souvik, welcome back to the Journal Club.
Happy to be back again. Thank you.
So, here I have a little picture about, the way I was taught is, if the p is less than 0.05 or less than or equal to 0.05, then there's an association or effect. And if it isn't, there's no effect. And so is it really that simple? Is that kind of the way in which we should be thinking about p-values and results from studies?
So p-value, as we all know, has been a key part of statistics in health research. And the p-value is the most commonly used measure to test whether the results of an experiment are statistically significant. And a p-value of less than 0.05 has been conventionally used as the threshold of statistical significance. But the scientific community is increasingly concerned as p-values are often misinterpreted, over-trusted, and misused, which is probably not helping scientific progress. So to answer your question, it shouldn't be that simple.
So how did we get to this kind of p equals 0.05 threshold? Where did that come about, and why is it still so widely used?
Now, healthcare research mostly revolves around trying to conclusively prove if intervention A is better than intervention B, or if exposure to factor X is worse than exposure to factor Y. Now, based on the design, researchers will use different statistical models to establish or refute their hypothesis. And the most commonly used statistical approach is the null hypothesis significance testing, where the underlying assumption is that there is null or zero difference between the two interventions or exposures of interest. Now, the p-value is defined as this probability of getting a result equal to or more extreme than what was actually observed under the assumption of no effect, that is the null hypothesis. Now, this definition sounds a bit too complicated for a lot of us. So in simpler terms, a p-value is a measure of the compatibility between the observed data and the statistical model used to compute it, ranging from 0 for complete incompatibility to 1 for perfect compatibility. So smaller the p-value, the more unlikely it is to get the observed results in a world where the null hypothesis is true. But we cannot completely rule out null hypothesis. So we pick a threshold for p-value below which we can confidently reject the null hypothesis. And a convenience threshold of 0.05 for statistical significance was first introduced by Sir Ronald Fisher in his book, Statistical Methods for Research Workers, back in 1925. Now, Sir Fisher did highlight that if an odds of 1 in 20, which essentially translates to a p of 0.05, did not seem high enough for your question, other levels of significance may be used. But that somehow got lost in translation. So all grad schools have continued to teach that by convention, if there is less than a 5% chance of seeing the observed or more extreme results of the experiment, assuming the null hypothesis is true, the results are usually considered statistically significant.
So what I've put up right here is actually tied in really closely to what you just said, which was actually when the American Statistical Association about 5 years ago put out a statement on p-values. They actually started with this conversation that was on one of their chat boards about this issue of kind of how we've come about to this threshold. And you did define you gave a nice definition of p-values. This is one in which you can see here, this is how the American Statistical Association gives kind of a general definition of p-values. And I wonder if, one of the common things is whether we think of the p-value as kind of the truth of a null hypothesis. And this is also in their statement, they kind of touch on this, but I wonder if you can kind of talk a little bit more about this idea of the p-value, being kind of a measure of truth.
Yes, so a p-value is often misinterpreted as the probability of the null hypothesis being true. And we have all made that mistake at some point. For example, if a p-value threshold of significance is 0.05, it may seem that there is a 5% chance of the null hypothesis being true, isn't it? But for any set level of significance, the probability of the null hypothesis being true could very well depend on the proportion of true hypotheses being tested. Now, there is a wonderful tutorial by Francis Perry Wilson, a nephrologist from Yale, where he nicely explains this concept. Say in a world with 50% true hypothesis, a p-value threshold of 0.05 gives us roughly a 6% chance of obtaining a false positive result. But if we start testing a lot of hypotheses and find ourselves in a situation where, say, only 10% of the hypotheses are true, then a p-value threshold of 0.05 will still leave you with about a 36% chance that the null is true. So the p-value does not really represent the probability of the null hypothesis being true.
So, one of the things that the American Statistical Association, the statement said, and here's a quote verbatim, is this idea of not making conclusions just based on p-values at a certain threshold, even though that's what we do. And there's been a call and a commentary in Nature about this idea of actually retiring statistical significance testing. And I wonder if you can talk a little bit about that.
Yes, so problems have been flagged with p-values for years, as you just mentioned. Scientific journals still continue to value statistical significance, sometimes even over methodological rigor as a criterion for publication. And this has been unfortunately exploited by scientists, which has led to this rather undesirable practice of p-hacking, where researchers would conduct multiple analyses and cherry-pick the findings with a p-value of less than 0.05 without a full disclosure of the number of analyses conducted and the number of hypotheses tested. But as John Ioannidis rightly puts, an extreme measure of getting rid of p-values completely without a viable alternative solution could create a state of statistical anarchy. So the solution better lies in using p-values more appropriately rather than completely retiring them.
So one thing that Ioannidis, highlighted as a potential alternative is actually lowering the p-value threshold, maybe making it a little bit more conservative. Instead of 0.05, making it 0.005. And I wonder what your thoughts on that are as it relates particularly to our field, where we often do trials in preterm babies. There at any given center are only so many very preterm or extremely preterm infants. And I wonder if you could touch on that idea of should we really be trying to move to even lower thresholds, maybe to reduce the chance of spurious findings? Yeah,
so eminent researchers like Ioannidis have proposed to lower the p-value threshold for significance from 0.05 to 0.005. And the results that fall between these two thresholds will then be termed as suggestive. Now, it is estimated that moving the p-value threshold from 0.05 to 0.005 will shift about 1/3 of the statistically significant results of past biomedical literature to this category of suggestive. And this may prompt researchers to further investigate the hypothesis with more robust research designs and larger sample sizes. And this will also prompt us to scrutinize the evidence a bit more closely before incorporating them into guidelines. But there could be problems. In order to achieve that coveted statistical significance, some researchers might move away from patient-important outcomes and start selecting surrogate endpoints of questionable clinical relevance, which is already a problem in neonatology. And another problem with our field is that, like it or hate it, we often have to be content with small sample size trials. So we are often left with borderline or non-significant p-values despite large effect sizes. So if we lower the p-value threshold further, there's always a risk that the true treatment effect will become non-significant and therefore ignored.
And just to highlight the point you made, I pulled here, this is actually from the whole body hypothermia trial conducted by the Neonatal Research Network, arguably one of the most important studies in the last couple of decades in our field, large treatment effect. And if you looked and said, what if we powered this study for kind of a p-value threshold of 0.005 or an alpha of 0.005, you would have needed, almost, 70% plus more of the sample size than initially studied. That would have been a longer study, potentially longer years before this therapy became implemented into practice. And so I agree with you. I think there is this trade-off of lowering a threshold in terms of the implications it would have on feasibility of studies, the duration of studies. And in this Nature commentary, they highlight some of these ideas of kind of being careful about false conclusions, particularly this conclusion of the absence of an effect or no evidence of an effect. They went on to look in the sample of 791 articles across 5 journals, where a large proportion of these articles were wrongly interpreted, and this issue of kind of not meeting statistical significance, meaning there's no evidence of effect. Thanks, Souvik, for joining this time, and I look forward to continuing this conversation and transitioning from p-values to a discussion on interpreting effect estimates. So stay tuned for our next EBNEO Journal Club, episode 8. And if you haven't, subscribe below, and that way you can be updated when our new Journal Club comes out. Thanks for watching.